Welcome to India's most comprehensive e-learning platform, Byjus Exam Prep. In this evening, we all have gathered together to discuss one of the very important topic in measurement subject as a part of the Champion series. So far, we have discussed several lectures and several subjects related to Champion series. However, this is the last lecture in measurement subject, especially in the Champion series. As you all were repeatedly asking to take the class on the Q meter, I came up with a special topic, that is Q meter. Today we will going to discuss all different types of questions that are possibly associated with the Q meter. As long as you are with me till the end of the session, I am very sure you will definitely get full out of full marks from the Q meter. The only thing you must have is a patience till the end. Well, before going to address the concept related to the Q meter and the associated questions of the Q meter, let me quickly and briefly explain about myself. So as you all can see, maybe the new students, they might not be know about myself. So myself Phanindra, and as you can see, all put together, I have an experience of 12 plus years in teaching, especially for engineering aspirants as well as GATE aspirants. Up to now, I have guided more than 50,000 students, and especially in the subjects of control systems, circuit theory, measurements and industrial instrumentation. And I am specially known for industrial instrumentation. Moving ahead with the topic Q meter, I feel that Q meter, even though it is very simple topic, really speaking, I don't know why every time IIT is so fascinated about this topic. Because in the recent years, I have been constantly observing several questions related to Q meter. So today, we will try to understand all different possibilities of questions, especially in the Q meter. Okay. So moving ahead, this is the schedule what we followed and what we are still following, especially in the measurement subject. It starts with the 2 watt meter method. That was the first class I have taken in the measurement subject as a part of Champion series. After that, we have discussed in the second lecture, that is energy meter. And now we are here to discuss the third topic, that is nothing but Q meter. So let's try to understand what is the Q meter and what is the working principle of Q meter, applications of Q meter and all other associated questions of the Q meter one by one as a problem by problem. Clear? So moving ahead to the first question here. So all of you can see, I think people are in the festival mood. Every one of the, students are in the festival mode. Fine. Anyway, let me see the first question here. So Q meter works on dash principle. It seems to be very simple question. I too agree with that because most of the students immediately they can answer. But my intention is to explain the concept behind this, right? So there are 4 options. One is electromagnetism, second one is induction, third one is series resonance, and fourth one none of the above. And this is the way how classical and recent digital Q meter looks like. This is considered as a digital Q meter. However, Q meter can be of varieties of type, and some people call this Q meter even as, look at that, this same Q meter we can also call this as a LCR meter. So what do you mean by LCR? Of course, it is nothing but inductance, capacitance, resistance. It means that if you can address the quality factor of a coil, then we can measure the value of inductance and capacitance and resistance of the same coil. That means select a random coil here. So if I select a random coil like this, so assume that this is the coil here, right? So if it is a coil, and I am very sure that this particular coil, definitely it will going to have resistance, though people sell it to you like a coil. If you decode this electrically, it will going to have a simple resistance and followed by inductance property, right? These two things every instrumentation student and electrical students, whoever are there in the circuit branch, they all know about this, correct? They all know about this. Now my question is, if you look at this as resistance and this as inductance, for God's grace, so this is considered as a practical representation of the coil. But what is more important to know here is, whenever the current is passing through the coil, obviously it will circulate like this. It will circulate in each and every turn and finally come back to the other terminal, correct? It circulates in each and every terminal and finally come back to the other terminal or outer terminal or at last, correct? So when the current is flowing in this way, and I am very sure that huge amount of magnetic flux will come like this, correct? But even before that, I would like to tell you this point. This is current carrying terminal. So it is a conductor. Obviously, this whole turn will also act like a conductor here, correct? So now from this conductor to this conductor, definitely there is a gap here, correct? So therefore, how it looks like? It looks like two different conductors are there, and between two conductors we have a space. Therefore, this is considered as a distributed capacitance of the coil. So that means practically you need to show the distributed capacitance of the coil as C here. Clear? So that means whenever you buy coil, naturally the coil will have resistance, inductance and capacitance, and the capacitance which is distributed all over the coil here, it is considered as a CD. Clear? So LCR meters or Q meters are specially designed or are specially equipped to measure all these variables, that is inductance as well as capacitance as well as resistance of the same coil, that is R, L and CD. So sometimes we call this as the distributed capacitance, sometimes even the normal capacitance also we can find by using the Q meter. So today we will see all our questions in the orientation of measurement of R, L and distributed capacitance of the coil. But anyway, this is not our question. What is our question? Q meter works on dash principle, correct? So let me show you how exactly the Q meter looks like. This is exactly the way how the Q meter looks like, and let me come from the back side. We are going to have an oscillator here, and this oscillator, right, so it will going to generate some voltage. Definitely it will going to generate some voltage, and that will definitely be sinusoidal signal, correct? So what we are going to do is we are selecting resistance. In fact, the shunt resistance must be very high here, and we are taking the voltage across the shunt resistance, and usually and ideally we expect that this resistance must be as less as possible, so that this E is equal to the voltage across the oscillator. Clear? In fact, I should say ideally this E is nothing but the voltage across the oscillator, and to measure the supply voltage we are using a thermocouple based voltmeter which is going to measure the voltage across the oscillator. So therefore, let me call that E as a supply voltage here for time being. Let me call this as a supply voltage here. Correct? This is considered as a supply voltage. Fine. Now most important thing is supply voltage is on side, and there are two terminals here, T1 and T2 here. Correct? So this is considered as a test pair or test terminals where we keep our coil. But you must remember this point every time whenever I say coil, it will have resistance, it will have inductance, even this coil may have the distributed capacitance also like this. Clear? And I have clearly explained what is the meaning of distributed capacitance. That is, between turn to turn of an inductor, we are going to have a small capacitance, and that is considered as a contribution of the distributed capacitance. Clear? So moving ahead, here we have one port, and here we have one more port, that is T3 and T4, and especially between T3 and T4 we have a capacitor, and this capacitor is called as a tuning capacitor. Clear? And interestingly, as we are tuning this capacitor, we know this value all the way. It is a known value. Clear? Because it is there in our hand. It is there in our hand, and we know what is the value of the capacitor, because we will tune the capacitor value in the front board. Here if you can see, here we will change the value of capacitor so that we will be able to know what is the value of E. Clear? At the same time, we are measuring the voltage across the capacitor, and this voltage across the capacitor I am calling this as a EC here. Clear? That is EC. And how do we measure the voltage across this capacitor? We are measuring this voltage across the capacitor with the help of electronic voltmeter here. Clear? With the help of electronic voltmeter. I hope you understood this. Now, how does this particular device functions? This particular device functions based on the series resonance here. So let me write down this as a series resonance. What series resonance says? Of course, I am not going to discuss about the detailed description related to the series resonance. Definitely that is not our part, and that is not our requirement in this particular lecture. Series resonance means you must understand the voltage across the capacitor EC. If I say that is voltage across the capacitor, that must be equal to Q times of the supply voltage. Clear? Voltage across the capacitor equals to Q times of the supply voltage. Same thing will happen even across the inductor also. Clear? So now how do we find the value of the quality factor here? So the quality factor could be written as the value of the voltage that is across the capacitor divided by the value of the total supply voltage, and this can be done only at resonance. Please make it this condition very clearly. This can be done only at the resonance. Interestingly, the resonance frequency can be given as omega is equal to 1 divided by under root of L into C, where L is the inductance of the coil here. Of course, C is nothing but the capacitance of the coil, and we are varying the value of capacitor such that we will face the resonance here. We will get the resonance there. Clear? So people do call this as the resonance frequency omega R, and if you want frequency in terms of omega is equal to 2 pi f, so f is equal to omega r by 2 pi. So both the way we can write down here. Clear? So that means I can say the quality factor is equal to EC by E, and in another word, people do say that the quality factor is equal to 1 divided by omega into RC here, where R is this resistance and C is the capacitance and L is the inductance. So in fact, this is considered as a quality factor, and ideally the quality factor should be equal to what? Omega L divided by R. Clear? This is what we are expecting. These are ideal values. In fact, this is the true value I can say, and even this is also true value here. So how do we get the value of omega? Of course, the value of omega will come from here. If you know the value of omega, and if you know what is the value of your capacitance, then we can calculate the value of the quality factor. Once you know the quality factor value here, then we can aim to calculate the inductance. Clear? This is the way how the inductance will be measured. However, we should have little bit patience to understand the concept in the better way, right? So moving ahead, I hope you understood what is the meaning of series resonance. So therefore, what would be the correct answer here? Option C is the correct answer for this question, that is series resonance. Now let's move on to the next next question here. So next question is, Q meter is used to measure dash. Okay, there are 4 options. Of course, all 4 options you know, right? So I already told you that Q meter is generally called as what is Q meter? I told you that the Q meter is called as LCR meter. Means it is capable to measure inductance, capacitance and resistance. So of course A and B and C, all these are right. Capacitance it can measure, it can even measure the distributed capacitance also. How it will be possible? Now that I will explain with the help of questions. Suppose first of all, look at this, the overall setup of the Q meter. Let me explain how does we will be measuring the quality factor first. Clear? How we will be measuring the quality factor. So the very first application is measurement of quality factor. Let me write down here. All of you please see. Measurement of quality factor. Let me show you how exactly we measure the quality factor. We all know that when we connect a coil like this, coil will have a resistance and inductance. No doubt about that. If it has a resistance and inductance, and what we do is we will tune this particular capacitor to some value. That means this value is known to you now. This capacitance is known to you because you are only changing its capacitance such that the resonance will occur. What is the resonant frequency here? First of all, as I said, the resonance frequency can be written as 1 divided by under root of L into C. This is of course without any doubt it will be in radian per second. This is one side story, but when you look at FR, that is a resonant frequency FR in terms of hertz, how can I write this one? This will be like omega R divided by 2 pi, and people do call this as or do write this as 1 divided by 2 pi under root of L into C. It is going to be hertz. Clear? That is considered as a resonant frequency here. Good evening, Rajshekhar. Very good. Option C is the correct answer. Excellent. So FR is equal to 1 by 2 pi into under root of L into C. That is called as a resonant frequency. Clear? Now I have 2 more questions here. Just look at that. You know the value of you don't know the value of L, or you don't know the value of C. Sorry, you know the value of C. C is known to you. Correct? At the same time, you are going to set the resonant frequency. Assume that you might be knowing the resonant frequency. Then how do we get the quality factor? Of course, the true value of the quality factor, it must be equal to omega L divided by R. Excellent. But can you please see what is the measured value of the quality factor here? So let us look at the measured value of the quality factor. Measured value of the quality factor will be different. Why? Have you seen this resistance and the shunt resistance? Of course, this resistance and the shunt resistance both will be coming in contact. In fact, both will be connected like in series configuration. Correct? R shunt here, this resistor and this resistor, both of these two are actually looking like connected in series configuration. Then when we measure this quality factor, you will be having like omega L divided by R shunt plus R here. Clear? R shunt plus R. Therefore, if you take R outside, what you will going to get here? Look at that, omega L divided by R we can take outside, and if I can take this outside, it will become like 1 plus, 1 plus, it will going to become like 1 plus R shunt by R. Am I right? Just look at that, R shunt by R. Now the great part of this is, what is omega L by R? Can you tell me what is omega L by R, Rajshekhar? So omega L by R is considered as a true quality factor divided by 1 plus shunt resistance here divided by R here. Clear? So this is exactly the way how the relation between the measured quality factor and true quality factor both looks like. So always when we measure the quality factor of the coil, we will be getting a error value. Definitely we will be getting error. Why? If it is a measured value, that is a true value, and we cannot exclude the value of R shunt. R shunt will be always there. Clear? Now let us look at the other side of the same coin here. So how do we estimate the value of inductance here? Can you tell me how do we get the inductance here? Simple. Let us square this value 1 by 4 divided by pi square, of course, into L into C. Right? Then L can be written as equal to 1 divided by 4 into pi square into FR square into C here. Clear? So this is considered as a value of inductance. Clear? So you know what is the resonant frequency, because when we are tuning this capacitor, a beep sound will come at resonant frequency. That means the frequency will keep on change in the front panel. When we are changing the capacitors, the frequency will change, and at one particular value of the capacitor, you will get a beep sound, and you can see what is the resonance frequency that is obtained on the meter itself. So therefore, resonant frequency is easy to calculate. Once you know the resonant frequency, just keep here to calculate the value of inductance. So I explained the way how we will be getting the inductance value, how we will be getting the quality factor. Both I have explained so clearly here. Now let us move to the next level by following some questions here. Clear? So look at that. There is a question here. Let me show you how to address this question. A coil of resistance 10 ohm. What is this? This is, first write down like this, the R value it is, correct? So let me write down R value is equal to 10 ohm, because the coil resistance is 10 ohm. Is connected in the Q meter circuit between the terminals T1 and T2. This is very important. That means go ahead with the circuit. This is T1 and T2 and the coil is connected here. So that means it will also have some inductance. Fine. Resonance occurs at a frequency of 1 megahertz. This is what I was saying. You will be always knowing the value of resonant frequency, and we will tune the capacitor because inductance value is not known to us. So we will tune the capacitor such that we will get the resonant frequency. Clear? So therefore the resonant frequency of this circuit now, it could be written as 1 into 10 to the power of 6 Hz, that is considered as a 1 megahertz here. Clear? Now let us look at that with the tuning capacitor set to 65 picofarad. What does it mean? Now the capacitor value, it is equal to 65 picofarad. 65 into 10 to the power of minus 12 farad here. Correct? So moving ahead, the calculate the percentage error introduced in the calculated value of the quality factor if the resistance is, or if the resistance of 0.02 ohm is used across the oscillator circuit. Excellent, right? So that means R shunt here, now its value is given like 0.02 ohm. Clear? R shunt value is given like 0.02 ohm. Be clear with this. Such a less value, isn't it? Right? Anyway, let me move ahead with this. And what is the measured value of the quality factor? As I said, measured value of the quality factor is equal to the true value of divided by 1 plus. What was the value earlier we have calculated? Shunt resistance divided by R, right? So let me write down shunt resistance here divided by R here. So how much it will become now? Measured value is equal to total quality factor true value divided by, of course, 1 plus. What is the value of this one? 1 plus R shunt divided by R. What is the shunt value? That is 0.02 and divided by 10 here. So it will be 0.002, right? So therefore I can say its value is equal to 0.002 here, correct? So yes, then what is the final value here? 1 plus 0.002, and you have to take the inverse of this one, right? So you will be getting 0.998 into QT. So measured value of the quality factor is equal to 0.998 into true value of the quality factor. Now you must know what is the value of the true value of the quality factor. How do we find the quality factor, true value of the quality factor? Simple, see, the true value of the quality factor can be written as equals to 1 divided by 1. In fact, this can be written like this also, isn't it? Just try to apply your common sense here. So quality factor of the coil can be written as omega into L divided by R, correct? You may be arguing with me, sir, I don't know the value of L here. No problem, we will try to estimate that because R is known to you and omega is also known to you, right? So this can be written as 2 into pi times of FR, that is the resonant frequency, because this is also resonant frequency here, omega R, and L. You don't know what is the value of L here, correct? No problem, let me write down the value of L as like this only, and let me write down R value as 10 here. Clear? The true value of the coil capacitance is 10. But at the same time, this is also can be measured in the simple way from this relation also, correct? 1 divided by resonant frequency omega R, right? In fact, this can be written like this because capacitance value is known to us, so it would be easy for us to evaluate everything from the capacitance side, correct? 1 divided by 2 into pi into FR, that is omega R, 1 divided by omega R into resistance value into capacitance. This is the way also we can find the value of capacitance, isn't it? So therefore, if you go ahead, how do we get the true value of quality factor now? Now the true value will be equal to 1 divided by 2 into 3.14, and what is the FR value? That is the resonant frequency value, that is 10 power 6. So let me write down 10 power 6 into the resistance value. How much that is? 10. Very good. 10. What is the value of C? 65 picofarad. So let me write down 65 into 10 power minus 12. Clear? Now I am leaving the homework to you, because if you solve this, you will be getting the true value of this one, correct? So let me make it very quickly. What is the true value here? Because many people may not be able to get this one. So 3.14 into 10 here and then 65 here, correct? So 4082, right? So it will be like 1 divided by 4082, and what will be there in the numerator? 10 power 6. So such a very high value, right? 1 divided by 4082. Let us see what is that. 1 divided by 4082, it will be equal to 2.44 into 10 power minus 4. So it will be all the way equal to 2.44 into 10 to the power of 2. So therefore let me write down quality factor. Now it is equal to 244. In fact, this is considered as a true value of the quality factor, very high, correct? True value of the quality factor is 244. Is our question is completed? No, we need to calculate the error in the quality factor measurement. So how do we do that? True value is known to us. Now what would be the measured value now? So can you tell me what is the measured value here? So interestingly, if you want to look at the measured value, this is not so difficult. So only the thing you need to have patience. That is, measured value is equal to 0.998 into QT. So what is the value here? So let me write down 0.988 into QT is how much? 244. So all the way you will going to get 243.5, right? Approximately. I'm taking approximate value, so don't worry so much about these values. Now true value is known to you, measured value is known to you. Then how do we calculate the error here? So percentage of error. Is it the question is percentage of error? Yes. Question is all about the percentage of error. So how do we get the percentage of error now? It is also very simple. Just you need to have patience till the end, as I was saying. Right? Percentage of error would be considered as equal to measured value minus true value divided by true value into 100 here. Correct? Into 100. What is the measured value? Can you tell me? Look at that. What is the measured value here? That is 243.5. So let me write down 243.5 minus, what is that? It is going to be 244 whole divided by, again true value is 244 into 100. So finally we can say here that as 243.5 minus 244 all the way. So you will have some value divided by 244 without any doubt and into 100, correct? So at last you will be getting the value as minus 0.2%. This is your final answer to this question, minus 0.42, minus 0.2, clear? So Clement, Aldo, you got this value, see, minus 0.2% is the final answer, and that is the correct answer for this particular question. Hope you got it, right? Now moving ahead to the next one, but before going to the next question, I would like to tell this point. Most of the students, what they do is, they will write this value, that is Qt is equal to omega r into L by r. But the problem is, they know the value of r, they know the value of omega r, but they don't know what is the value of L. They don't know what is the value of inductance. That is where they will stop. But go one step ahead, the quality factor can also be written as 1 by omega into RC, correct? So because capacitance value is always known to you, because you are tuning the Q meter, and if you look at this diagram, in this it is a tunable capacitor, means this value is known to you. That is the advantage here, clear? So now moving ahead to the next question. These kind of questions are so popular here. So let me take some time to explain this question. Even I have seen multiple times these questions in the GATE exam also. The question is, in a Q meter setup, right, the distributed capacitance of a coil, see, look at the statement clearly. Distributed capacitance of the coil is measured by changing the capacitance of the tuning capacitor. Very good. So that means we are changing the tuning value of capacitor to find the distributed capacitance. Well, the values of the tuning capacitors are C1 and C2 for resonant frequencies F1 and 2F1 respectively. The value of the distributed capacitance is dash. So this question, if I am a student, I will think like this. In this question especially, distributed capacitance is there. Where will be the distributed capacitance? Look at this diagram. I already told you several times the distributed capacitance will be across this coil here, correct? So let me draw that so that some of you will go and many of you will get the idea here. So let me write down, right? So here we will be having distributed capacitance. Let me write down that as a CD here, right? Now the great point here is, when you write this as a CD here, so CD will also participate in the resonance. Earlier, when we don't write CD, we have simply taken that resonant frequency is equal to 1 divided by under root of L into C. Correct? This is what we have taken when there is no distributed capacitance. When there is no distributed capacitance in the calculation. But if the distributed capacitance is there, how the overall equivalent capacitance will come? Now you see, if you take these two terminals, right? So look at that across these two terminals, and if I short circuit this and find the equivalent capacitance, if I short circuit this and find the equivalent capacitance, and I am very sure that this capacitance and this capacitance both will come in parallel whenever you short circuit this. That is called Thevenin capacitance, right? So just short circuit this one, then you will understand. So this capacitance CD and this capacitance both will come in parallel. That's why without any second thought, I can say, if you don't believe me, you can see, suppose when I short circuit this, what will going to happen? If it is T1, this is going to be T1. As it is short circuited, this will become T1 and this will become T1 here, and even this one also will going to become T1. Correct? So and anyway, this is going to be now T2 here, and this will become T2 here, and this will going to become T2. What does it mean? This capacitor is between T1 and T2. Even this capacitor is also between T1 and T2. What does it mean? It means that both of these two capacitors are connected in parallel configuration. Correct? So therefore, if you consider the distributed capacitance, you don't have the right to write like only C here. Rather, you should include the distributed capacitance also here, that is C plus CD here. This is considered as your resonant frequency. And in case if you are not interested to write in sorry, omega r, rather you can even extend this and put it in a simple word like 2 pi into all this by looking at frequency. In fact, that is considered as a resonant frequency. So every time we need not to write like FR. So let me make it simply like F here. Clear? Now what is our question? What is our objective here? So we are discussing so many things, but what would be our objective here? Our objective in this question is to calculate the value of the distributed capacitance. Clear? How do we get the distributed capacitance? In this, what we do is, we will not change the capacitance CD. We will fix the capacitance there itself. let the capacitance CD is there, but we don't know what is the value of CD. We don't know what is the value of CD. So what I do is, I will change this capacitance to some value called C1. Okay, let me change this value of capacitance to C1 such that I will get the resonant frequency F1 and the value of tunable capacitance is C1. Clear? Next time what I will do is, now this value is known to you, because resonant frequency will be always known to you as you are working with the frequency meter, that is Q meter, correct? So this will be known to you and you are tuning this value. C1 is known to you. L, that means inductance, you may be knowing, you may not be knowing, that is not the matter. What I will do is, this is a step 1. In step 1, intentionally I am changing the value of capacitance to C1 such that F1 is noted or F1 is achieved. After this, in the second step, brilliantly what people do is, in second step, this is really crazy, please see. Step 2, again I will change the capacitance. That means first step is over, fine. So let me forget about this one now. Again in the second step, once again I will change the capacitance C from initial value to C2 such that I will record the value of F2 which is twice than the F1 here. Clear? Which is twice than the F1. But however, what would be there? Again, this is also a resonant frequency, right? So what should I say here? 1 divided by 2 pi under root of L into, inside the bracket we can say, now the capacitance is tuned to C2, correct? So let me say this is C2 and here the distributed capacitance will be there. Clear? So the distributed capacitance will be there. So let me take some margin here. Clear? So that means second time what we have done is, we have changed the value of capacitance from C to C2 such that we will get a new resonant frequency which is equal to twice the previous frequency. Clear? But one must really understand in this case, F2 is equal to 2 times of F1. That is what we got it here. So now let me move on to this one. What is the F1? First of all, in first case, step 1, let me write down. Step 1, I told you that F1 is equal to 1 divided by 2 pi into L into C1 plus CD. This is what we have seen, right? And step 2. In step 2, intentionally I have changed the value of capacitance such that in F2, we will be having like 2 pi into under root of L into, here you are having like C2 plus CD. And what was our condition? Our condition was very clear here, and even every one of you really understood that our condition is F2 is equal to, that is F2 is equal to 2 times of F1 here, correct? So what is F1 here? So I can say 2 times of F1 could be written as 1 divided by 2 pi into under root of, this will become like L into C1 plus in fact CD, that is F1. Don't forget about that one. This is F1, so I have replaced F1. But what is F2 here? Have you remembered this F2, right? So or else let me take one more step here for a better understanding. Let me erase this one because this step is required. That's why I'm writing here. Okay, right. So just look at that. F2 is equal to 2 times of F1. What is F2 value here? Do you have F2 value? Yes. What is F2? F2 is the value of the frequency that we got in the second case. What is that value? So this is equal to 1 divided by 2 pi into, look at that, 1 divided by 2 pi into under root of L into C2 plus CD, right? So and this must be equal to 2 times of F1. So let me write down here 2 divided by 2 pi into under root of L into, here you will be having C1 plus CD here, correct? So C1 plus CD here. Now one must really understand this clearly that 2 pi to 2 pi will get cancelled here. Now L will naturally get cancelled here, correct? So this can be written as 1 divided by C2 plus CD, and this side you will be having 4 divided by C1 plus CD here, right? So if you just square on both sides, this is what you will be getting here. And from this, can you write what is the distributed capacitance now? This is known to you. Therefore, I can say C2 plus CD, that must be equal to what? C2 plus CD, that is equal to C1 plus CD by 4. C1 plus CD divided by 4 here, correct? In fact, Once you get this value, you have to do small modification to get the final value. So how do we get that one? Again, this is not a big deal, but I feel that it is required to communicate these things. Okay, so C2 minus C1 divided by 4 here, correct? C2 minus C1 by 4, and here we have CD divided by 4 minus CD here, correct? So just try to rearrange both of these two, then what you will going to get here. So let me write down here. So it is 4C2 minus C1, right? 4C2 minus C1 here, and of course that would be equal to, here you will be having how much? So 4CD, 3CD, right, minus 3CD divided by, and minus 3CD, that's all, minus 3CD. From here we can say distributed capacitance CD is equal to C1 minus 4 times of C2 whole divided by 3. And of course, finally we got this value here, which is very useful, and most of the times it was asked in the question. It was asked in the gate paper. So what is CD finally? CD is equal to C1 minus 4C2 by 3. That is exactly what we got it. And we got this expression by taking F2 is equal to 2 times of F1. Remember that it need not to be only 2 times of F1. Anyway, you are changing the tuning capacitor. So sometimes we may get 3 times of F1 also, 4 times of F1 also, 5 times of F1 also. So you have to read the question carefully what they have given. They mention like F1 and 2F1. They may say that F1 and 4F1. If it is so, you have to take 4 here. If they say that F1 is equal to 8 times of F1, then you have to take 8 here. Clear? So that is exactly the way how you have to proceed to get the answer. I hope I have conveyed the information very clearly to you. Now moving to the next one. This is not a difficult question, and actually I want to give this as a homework question, but let me give the glimpse of this one. A circuit consisting of a coil means you require to identify something related to coil. Okay, a resistance and a variable capacitor connected in series is tuned to resonance using the Q meter. Okay, if the frequency is 500 kilohertz, okay, right, so that means the resonant frequency is given like 500 kilohertz. Because everything what we speak in terms of frequency, especially in the Q meter, that is definitely resonant frequency only. Okay, so resonant frequency is equal to FR, which is equal to 500 kilohertz. So let me write down 500 kilohertz here. First, number 1. What is the number 2 here? The resistance of 0.5 variable capacitor is set to 350 picofarad. Okay, so resistance is 0.5 ohm. And variable capacitor is set to 350 picofarad. Fine, 350 picofarad. I can say like this. Fine. So yes, and Q meter indicated the value of 90. So this is the measured value. So let me write down the measured value of Q meter here is equal to 90. Good. So then the effective inductance and resistance of the coil respectively are dash. So they are asking what is the value of R of the inductor and what is the value of L of the inductor. Clear? So first of all, measured value is 90. How do we get the measured value generally? Measured value is equal to omega L divided by the shunt resistance RSH plus R. Correct? This is what I was saying even earlier also. So if you go with this, that is resonant frequency is known to you. So omega can be written as a 2 pi into F. Of course, the resonant frequency R into L, you don't know L value, let me keep L itself. R shunt, what is the R shunt value? They have mentioned here that 0.5 ohm. This is the shunt resistance value because that is only available there. So let me write down this as a 0.5 here plus R. Very unfortunate that measured value of this QM is given like 90, but you don't know the value of L, we don't know the value of R. Two variables we don't know. In that case, the best way is to go to next one, that is even the measured value of Q can also be taken from here also, correct? 1 divided by 2 pi FR, that is omega R into the value of capacitance, right? And here we can take the value of R plus R shunt. Clear? This is still available for us, right? 1 by omega CR. From capacitor side we can calculate. The beauty of this is, you know QM. What is the measured value of QM? Indicated value of QM is 90. So let me take 90 here. If I take 90 this side, then what are the values you know? You know every value here, right? So from here, it's very easy for you to write. So R plus R shunt, we can take it say this way, and it will be equal to what? 1 divided by 2 into pi is 3.14. Of course, resonant frequency is how much? 500 kilohertz, 500 into 10 power 3 here, 500 kilohertz. And the C value, do you know what is the C value? C value is 350 into 10 power minus 12, 350 picofarad, 10 power minus 12. And we have to bring the quality factor also here. What is the quality factor? That is 90 here, right? Now if you do this analysis, you will get R plus R shunt, correct? But R shunt ka value aapko de diya. So what is the R shunt value here now? Shunt value of the resistance is known to you, that is 0.5 ohm, correct? Yes, very good, Aldo. So the shunt value of resistance is known to you. What is the value of the shunt value? That is 0.5 ohm. So if the shunt value is known to you and this side the value is known to you, from here we can calculate what is the value of R, correct? So what is the value of R? Easily you can do it. Once you get the value of R here, then come back here and substitute the value of R here. Then you will be able to get the value of inductance also. Clear? You will be getting the value of inductance also. The crazy part here is, as we don't know anything about the inductance, it is better to believe the capacitance and use the quality factor of the capacitance to calculate R first and then bring the value of R and substitute here to get the value of the unknown inductance. And this is a simple algebra that is left, and already Aldo has given the answer. So I sincerely request rest of all people, you try to work out clearly and get the answer. This is the homework to you. Almost 90% of the work I have done it. 90% of the work I have done it. I am just giving 10% of the work, which is simple algebra, because the engineering part I have completed. The core part of the question I have discussed. Only I am leaving a very simple part only for your homework. Okay. So do it and sincerely tell me. Aldo, if you complete, please let me know the answer. No problem. Now let me go to the next question here. Okay. This is also a good question. In fact, I should say, if a Q meter resonance is obtained when a variable capacitance is at 50 picofarad. That means the capacitor is tuned to 50 microfarad here, connected alone across the test terminals. Okay, right. So what does it mean? Look at that here. Let us bring back our, otherwise let me see whether the diagram is there here. No, right. So let us look at the diagram here. Yes, what it was said here is, this capacitance, because right now we are required to measure the capacitance. It is a third application, right? So what we are doing here is, we are trying to connect a test capacitance or unknown capacitance here. So let us say the unknown capacitance is CT. Clear? So whenever you connect this capacitance here, then again we need to tune this value to capacitor, right? Tune this value of the capacitor. So what they are trying to say is, first of all, when we don't have this CT at all, the capacitance is changed to how much picofarad? The capacitance is changed to 55 microfarad. Then only the resonance is occurred. That was the statement of the question. Correct? Let me remove this one here. And I was sure that the capacitance now, it is changed to 50 microfarad. That time, we got the resonance. Okay, we got the resonance here. So let me call this as C1, simply like this as C1. Clear? So this is C1. Now let us come back once again and look at the question here. Q meter resonance is obtained when a variable capacitance is 50 microfarad connected alone across the test terminals. So fine. That means right now the C is equal to C1, which is nothing but 50 microfarad. Excellent. So what is the resonant frequency here? FR would be written as 1 divided by 2 pi, of course, under root of L into C1, because the capacitance is changed to C1. Good. Next time, this is a step 1. Step 1. Clear? In this, no test capacitance is connected. Only tuning capacitance is there. No test capacitance is connected. It means that if you look at the terminal T3 here and terminal T4 here, what is there across the terminal T3 and T4 here? Right now between T3 and T4 we have only tunable capacitor only. Clear? Now in the second step what we are doing is, we will try to connect a test capacitance across the terminals. This is going to be the second step. Connect a test capacitance or unknown capacitance here. Connect a test capacitance here. Let me write down a test capacitance across terminals terminals T3 and T4. Let me show you what will going to happen now. So if you do in this way, only across T3 and T4, look at that, how exactly it looks like. This is T3 now, and this side a capacitance is this C. Of course, this is C here only, and here we are connecting one more capacitance which we don't know, CT. Clear? So this is going to be T3 here, and this is going to be T4. Same I can say this is T3 and this is T4. Now can you tell me, in the second case, first case we changed this value of C to C1 to get the resonance, but in the second case we need not to change the value of C to C1 to get the resonance, correct? Why? This capacitance is also will come into the addition here. That's why in the second case we require to change this capacitance only to some other value C2, such that we will get the same resonant frequency what we got here. Clear? So that means here the resonant frequency now in the second case would be written as Fr is equal to 1 divided by 2 into pi under root of L into, here it will become like CT plus C2, and where CT is the unknown capacitance for us. CT is the unknown capacitance. Aldo, can you tell me what is the value of C2 now? It is very simple. This frequency Fr and this frequency Fr must be same. Both are same. Then L value will be same and L value will be same. Then these two values will be equal. These two values will be equal if the value of capacitance C1 is equal to value of CT plus C2. Correct? This is so simple, isn't it? So therefore, what should I say here? So simply like C1 is equal to C2 plus CT here, and therefore CT will be equal to C1 minus C2 here. What is the value of C1? That is 50 microfarad. Second time it is going to be 30 microfarad here. Correct? So therefore I can say 50 microfarad minus 30 microfarad, all the way this will be equal to 20 microfarad, which is considered as a capacitance of the unknown value, that is 20 microfarad. Clear? So you might understood here there are few things we have calculated. If you remember in this particular question, let me show you from the starting. Right? So first I have explained the basis. After that I told you how we can measure the quality factor. However, whatever you do, you will not be getting the accurate value of the quality factor, and I told you what is the relation between the quality factor of the measured in terms of the true quality factor. Correct? This relation I have explained. After that I have even explained how do we calculate the value of the inductance of an unknown coil. Correct? This is done. And then what we have seen. After that I have clearly explained how does we are going to get the error and what is the error and calculation, something like this. And then we move to the next one. And here in this case, we came to know how we can calculate the value of the distributed capacitance. Correct? In this question, I shown you how to calculate the distributed capacitance. And in the next question, I told you how do we calculate the value of resistance of the coil. Correct? So in this question, resistance of the coil. In this question, distributed capacitance of the coil. In this question, I have shown you, I have shown you how to calculate the inductance of the coil, right? And in the last question, I have told you, right, how we can calculate the capacitance of the unknown capacitor, that is CT. So all four questions finally converged clearly to the applications of the Q meter. And now I can confidently tell you to every one of you, wherever you go, whatever the exam you write, whether those are PSU exams or GATE exam or some other exams, as far as the Q meter is considered, this is the only concept that exists, and all these applications related to Q meter I have covered very clearly in the all 4 to 5 questions here. Clear? Hope you really enjoyed this session, and this will really help you a lot in your GATE preparation. And once again I am saying that to get the regular updates related to the GATE coaching, I sincerely advise every one of you, please connect to the channel so that you will going to enjoy the real level of the sessions to the GATE level. Thank you very much.